another speaker. Second speaker of this session is Michal Zajaček, who will speak about missing bright red giants in the galactic center. So please, you can start and good luck.
Thank you very much indeed. I will share the presentation. Dear ladies and gentlemen, thank you for the opportunity to speak at this special RAGtime, and I will present our recently accepted paper about the galactic center and its late type stellar population or population of red giants. But first of all, let me congratulate to Professor Stuchlik because we haven't had the opportunity this year to meet in person. But as astronomers, I think, or astrophysicists, we were quite predictive last year, so we celebrated a little bit during last RAGtime, as you can see. So I hope in the near future, at some point, we can meet again in person. And also this contribution and paper is to some extent, one should say, a child of RAGtime 21 in Opava, because Annabella Araudo, I'm not sure if she's now in the audience, but she had a nice talk on truncation of AGN jets by their interaction with stars or stellar clusters. And she showed this image of a red giant or stars, which is orbiting a supermassive black hole here. And as it interacts, the red giant has a very loose envelope, and this envelope can be detached. And it can then flow with the jet, be accelerated, and of course it can give rise to, for example, proton synchrotron emission or high energy phenomena. So this is interesting by itself also for example, blazars or in general radio galaxies or jetted active galactic nuclei. But my question at this point was, and this is a figure from Barkov, that why doesn't this figure actually continue? Because here we have a stellar orbit which is crossing the jet, but why doesn't the star or stellar core emerge in this figure? So it looked to me a little bit unfinished. And I was curious to explore this more, what happens to the star after it emerges from the jet. And then I had what immediately came to my mind was the problem which started basically when I was born 30 years ago. So in this paper by Chris Zellgren, now from Ohio State University, they did observations at 2.2 microns. And basically she reported, a missing or a drop in CO bandhead emission. This CO bandhead absorption feature occurs in atmospheres of cool red giants. And it was expected, usually in textbooks, you find that in the bulge of the galaxy or in the galactic center, the population is pretty old. And you should have somehow these features associated with old red giants should be somehow increasing in terms of density. But they found, interestingly, that when you look at this CO bandhead strand as a function of distance from, well, in this sense, Iris 16, because at the time still Sagittarius A star was a bit obscured source. So Iris 16 is a group of bright stars. So they found that as you go to the galactic center towards, suddenly this CO bandhead strand decreases. And this occurs approximately at about 10 or up to 20 arc seconds, where one arc second is 0.04 parsecs. So within about 0.5 parsecs, you see this drop. And this was associated with the decreasing number density of red giants. And they already, as you can see in abstract, discuss some scenarios that the lack of CO absorption in the central parsec is including the destruction of atmosphere of late type stars by stellar collisions, the association of CO molecule in the atmospheres late type stars by central luminosity source or some other potential process. So this was an interesting problem from 1990s, and this is, by the way, Chris Zellgren who discovered it. So her real image, an image at 2.2 micrometers. And by the way, this wavelength is also important because most of the observations of the galactic center, including the motion of bright stars around Sagittarius A star, were done at this wavelength 2.2 micrometers, for which this year's Nobel Prize was awarded to Genzel, Guess, but indirectly also to other people who contributed to this, namely Andreas Eckart, Rainer Schürdel, and others. So coming back to the stellar population, looking at surface brightness profile of brighter late type stars, this is in contrast, this density, to young stars, because there are also young OB stars in the galactic center who have this increasing single power law profile, but late type stars have flat to decreasing profile. And this was also recently confirmed by Rainer Schürdel and co-authors who found that actually it's more complicated because fainter late type stars have also this cusp profile, so single power law, increasing surface density, but brighter light type stars have decreasing or flat surface density profile. And this is quite puzzling because so then one has the question, what mechanism is responsible for a stellar cusp of fainter light type stars and a flat core-like profile of brighter red giants? And Schürdel actually found from stellar population models that 80% of the stellar mass in the galactic center formed more than 10 billion years ago. And if you look at typical two-body relaxation time, it's of the order of billion years. So most of these stars, most of 80% of the stellar mass should be relaxed. And then you should have for all the stars, these old stars, a cusp-like profile, so-called Bacall-Wolf cusp with a slope of about minus 1.5. For stellar black holes, it can be even steeper. But interestingly, this is not seen for bright light type stars or bright red giants, only for fainter ones. And this was also found independently by Habibi and Gallego-Cano that inside 0.04 parsecs, one has 4 or 5 bright giants missing, inside 0.3 parsecs, 100 missing bright giants. And in general, inside about 0.2 parsecs, there is a limit on the atmosphere radius up to 30 solar radii. So it seems as if something could be distracting or ablating these giants. And during these 30 years, there were many proposals of mechanisms, tidal disruptions of red giants, or red giant accretion disk collisions, but actually it's required that one has denser clumps, because for normal accretion disk densities, this doesn't quite work. One of the most popular was collisions of red giants with field stars and compact remnants. So collisional destruction, this was proposed by Finney, Morris, also Genzel later, and mass segregation effect. So some kind of dynamical catastrophic event like an infall of a secondary black hole or of massive cluster, which can also lead to the core distribution of giants. But instead, so coming back to Annabella's talk, I finished this kind of image in my head that when the red giant with a loose envelope interacts with the kinetic jet pressure, upper layers can be clearly ablated. So this we show in the paper when we focus on the recent evidence of activity of Sagittarius A star, namely gamma-ray Fermi bubbles or bipolar radio bubbles. And then from the energetics, one arrives to energies somewhere between 10 to 42 to 10 to 44 ergs per second for the jet. And since at the time, most of these late type stars were there and formed. Of course, a long time ago, they could have interacted with this jet. So this is, of course, an artistic illustration of Fermi bubbles and the jet. And in Fermi-Lat satellite, actually, they analyzed the gamma ray distribution on the sky. And these Fermi bubbles are really huge. It's 50 degrees below and above the galactic plane. So if we had gamma ray eyes, it would be one of the largest structures we could see on the sky. And this jet appears like a linear brighter feature in the Fermi sky, gamma ray sky. So, and it's possibly also inclined, which is not unusual for jets to precess and change orientation. So of course, mathematically, one can derive the stagnation radius when one equates the jet kinetic pressure with the stellar wind pressure. And then one arrives at the characteristic stagnation radius of about 27 solar radii, which is consistent with the observational results on the upper atmosphere radius in terms of ablation. So for red giants, the stagnation radius can reach below their atmospheres and effectively ablate them. So here in the S cluster, if we plot the stagnation radius as a function of distance and jet luminosity, then within S cluster, typically we reach the stagnation radius between 4 to 30 solar radii. And then, of course, with these jet crossings, one has associated jet-induced envelope removal. So during a single passage, it's formally low, 10 to minus 10 solar masses. So it's this expression. But there are many crossings because the orbital timescales of these late-type stars is much shorter than the jet lifetime of 500,000 years. So then one has at least 1,000 to possibly 10,000 crossings. And during this time, the jet-induced envelope removal, including multiple passages, is comparable to cumulative red giant mass loss due to winds. So here we compare the mass loss, which are these inclined lines, with respect to general mass loss. So then it can affect stellar evolution clearly because the stars are losing more mass. And it's also comparable within S cluster to proposed star disk collisions mass loss, which was studied by Kiefer, Bogdanovich, and others. So within S cluster, this or 0.0 parsecs, it appears to be an efficient mechanism. And this was during one Seifert-like event in the galactic center. Of course, there were probably more events in the past. And so our estimates can be understood as a lower limit to this cumulative mass loss. Of course, it has an effect also on the appearance of stars, and this was the main point of the paper, because if you look at normal stellar evolution of a red giant in the Hertzsprung-Russell diagram, then the star is becoming cooler. But when at different distances from the galactic center it interacts with the jet, then it turns to the left, basically, in the Hertzsprung-Russell diagram, the evolution. So the stars becomes hotter, bluer, and appears younger. So it doesn't appear anymore as a red giant, effectively. And also in terms of a number red giants crossings through the jet per orbital period, it's also consistent with the basically roughly with the estimated number of missing bright red giants. So we calculated something like 3.5 within 0.04 parsecs and 100 within 0.3 parsecs. So this is purely the geometrical calculation. And then we also looked more at the surface density distribution. So we generated the Mog nucleus star cluster within 1 parsec of about 4,000 stars with initially single power law density distribution. So this is illustration, or basically our density distribution of the Mog cluster and the jet when it was active. And of course, if there is no jet, the population should stay rather cuspy, right? So single power law. But when you turn on jet, even with moderate luminosity, then the brightest giants basically become flattening in terms of their surface density. And if you reach 10 to 44, which was possibly the jet luminosity that led to the formation of Fermi bubbles, then for the brightest giants, you have essentially flat profile up to 10 arc seconds or 0.4 parsecs, and then it starts propagating also towards fainter fainter giants. So here you see that within S cluster also this 12 to 14 magnitude giants would have rather flat profile, but it doesn't touch the smallest or faintest red giants. So they still have basically power law, single power law density profile. And this is consistent with the general also observational findings that bright giants have a flat to decreasing profile, and fainter giants still have a cusp-like profile. So this is basically the main conclusion of our paper. Then in comparison with the no-jet scenario, the active Seifert-like jet, which was present a few million years ago in the galactic center, flattens the surface profile of the brightest red giants in the 10 to 12 magnitude bin, starting with the inner arc second, but for the most luminous jet, the core-like profile can extend up to 0.4 parsecs for the brightest giants. And faintest giants keep the cusp-like profile, so are not affected by the jet activity, because simply their atmosphere radii are smaller than the corresponding stagnation radius. And this, of course, also concerns young OB stars whose powerful jets can protect them in this sense from any jet that was present in the galactic center. And this is, of course, our scenario of the red giant jet interaction does not replace other proposed scenario. I think it could have well coexisted. Actually, I'm a little bit wondering why nobody has thought about this, because people were modeling, starting with Armitage, star disk interactions all the time. But of course, if you have disk around supermassive black hole, typically you have also a jet. So I mean, it's quite straightforward to also think about this scenario. But they have also different effective length scales, these mechanisms. While the star-disk interaction works best at further distances where the disk is gravitationally unstable, so the tumor criterion is less than 1. This mechanism, as we estimated in the paper, works best at smaller distances, so within a so-called S cluster, so where the fast-moving stars are located. Of course, at even small scales, one can have the tidal domain, so the upper layers of the big red giants can be stripped to some extent. So all these mechanisms could have contributed to the observed flat surface density profile of bright red giants. So, and of course, the paper is now was accepted by APJ and is on archive. So, of course, feel free to read it and send comments, because I think in the future, especially with Annabella, we would like to, some of the aspects of this study, namely the star-jet interaction, we would like to model it in more detail, because now we used mostly analytical, semi-analytical calculations, but we would like to look at this mechanism more from a MHD point of view, and also to calculate more precisely the stellar evolution, how repetitive star-jet interactions can affect the stellar evolution. So this is something to be still done, but the basic mechanism is now described basically. So thank you very much for paying attention.
Thank you, Michal, for your nice presentation. And now it is time for questions. So do you have any questions?
So if no one, can I have a question?
Yes.
Just 2 comments. It was a very nice talk, and at the beginning you had a lot of references, but now it came to my mind that we should refer also to Jim Dale paper about stellar collisions in the galactic center. It's quite a long paper, which was done actually in Spořilov some years ago.
Yes, I encountered this. I'm not sure if we are referring to it in the paper as such, but
I'm not sure now. But
yes, I think
red giants collisions he was discussing. But
I recall that paper because I think they basically what was discussed before analytically, these star-star or collisions. I think they simulated it using SPH, so indeed it's quite relevant. So we can at least include it, if not in this paper, in the RAGtime proceedings, I think. So.
Yeah, but the real question is actually these bright red giants, when they disappear from the cusp, which does not exist anymore for them, they of course should be moved to other types of stars, right? Which I think we haven't done yet. No, they should contribute to the cusp for stars which were not red bright giants, but they should be added somewhere.
Yes, you are right. It can work actually. I think also even in this Monte Carlo simulation of surface density profiles, what was happening that those brighter giants were to some extent contributing to the cusp of this fainter, because they were becoming fainter in infrared. So here actually we are creating a steeper cusp of fainter red giants by moving those brighter ones to fainter magnitude beams. So I think this was discussed to some extent in the paper, but you are right that also they are these old stars are made young in some sense. So I think we discussed this partially, but maybe it could be discussed in more detail how these stars could be detected potentially.
Yeah, because it's nice consistency check in a way.
Yes.
They disappear from one line, but they must contribute to the other line.
Yes.
Okay, nice.
So are there any other questions or comments? Yes, there is question from...
Is it Chris Schroven, I guess?
Oh, yes, so go ahead. You can just unmute your...
She's unmuted.
So there are probably some technical problems. So we probably thanks our speaker again, and if there will be some questions you can continue after this session. So
yes, so I think I can stay online as long as it will be needed. So thank you very much once again.
So thank you very much, and